Initial value problems are our first introduction into differential equations. And for some of you, differential equations may be on the horizon. It's good class. So again, notation, math's unceasing, incessant desire to use f of x for everything makes this a little more complicated than it needs to be. Every text is going to tell you initial value problems are dy dx equals f of x, so they can talk about the arbitrary f of x. And I'm going to say, don't do it. Don't let it be. Think of it this way: as we're used to looking at dy dx and saying, yeah, that's the derivative. That's f primed of x for some arbitrary function f. Or dy dx as the derivative of some function y is y primed. And that, it turns out, will be, I think, a much more intuitive way of doing this. Okay, so without even telling you what an initial value problem is, let's just tell you the method. You integrate both sides of a differential equation. So a differential equation is going to be something that has a differential expression in it, like the derivative, and then use some provided initial condition to solve for c. Okay, that was pretty brief, wasn't it? But let's look at this. What if we have dy dx equals, and leave yourself a little bit of room, f primed of x? Well, I just said you integrate both sides. Well, if those are both expressions in x, as we can see in both notations, then we could integrate. Oh, sorry. There's a golden rule of math says you can do whatever you want as long as you do it to both sides. And you can integrate with respect to x on both sides. And look at the right side. What is the integral of f primed dx? In other words, we have a derivative and we're looking for the function that gives us that derivative. Well, if our derivative is f primed, the function that gives us f primed as its derivative is f of x. Okay, and on the left, the derivative of y with respect to x is what the dy dx says. So we're asking the question, what has the derivative of y with respect to x? Well, just y. The function y has derivative dy dx. To see this, sorry, that keeps happening. To see this, remember, that's alternate notation for y primed. So you basically say, okay, the derivative of y primed is the derivative of what function? Well, just y. And that's the magic of a initial value problem. That's all that's going on. However, when we integrate, we introduce an arbitrary constant. And so we need to solve for that with some provided initial condition. So let's take a look at an example before we talk about the arbitrary anymore. Okay, so they give us dy dx is equal to 6x squared. And so in their notation, there's your f of x. But you know what? That's not f of x. That is some derivative. So let's call it a derivative. Let's think of that as f primed of x or something. Just emphasize that that's a derivative. Okay, so you take that initial thing and you integrate both sides. So the integral of dy dx is equal to dx. The integral of dy dx with respect to x is equal to the integral of 6x squared with respect to x. So the right-hand side we know how to do with a power rule. Add 1 to the exponent, drop down and divide by that exponent, and then tack on your c. The left-hand side, though, remember, this is really just y primed in disguise. So y primed is the derivative of what? Well, it's the derivative of y. And I'm just using function notation because what is y usually a function of? Y is usually a function of x. And so y of x means the function y with respect to x. And so sure enough, y of x equals some output. Now that's great. We've got an expression. We're pretty happy with that expression. We could tidy that expression up a bit. 2x to the third power plus c. We don't like that c because that means we have an infinite number of possible solutions and we want a concrete single solution. So now we use the provided initial condition y of 1 equals 5 to solve for this thing. So start with your function, make a substitution, y of 1. Okay, on the right-hand side, that's going to give us 2 times 1 to the third power plus c. But remember, y of 1 is the same thing as 5. That's what the initial condition is. And so we can replace y of 1 notationally with 5, and then we've got ourselves an equation in terms of just a single variable c that we can solve. And so we see that c has to be 3, and we get a conclusion. Reverse that substitution into your antiderivative, and you're done. Hopefully that didn't seem quite so bad. Let's take a look at a more, well, let's call it what it is, a more wordy example. So we've got a car that's traveling at 88 miles an hour. Oh no, it's not 88 miles per hour. It's too bad. We could have gone all Back to the Future on it. Showing my age. A car is traveling at 88 feet per second, which is the equivalent of 60 miles an hour when the brakes are applied. The car decelerates at a constant rate of 15 feet per second squared. How many seconds before the car stops, and how far does the car go before it stops? So what are we told here? Decelerating. Decelerating is about acceleration, but it's the opposite of acceleration, or it's negative acceleration. So they tell us a of t equals negative 15 feet per second squared in here. And now I don't have any variable t there because it's a constant deceleration rate. It doesn't matter what time the car stops at a constant rate of deceleration. Okay, so this is basically all we need to start. And then we'll worry about the initial condition or something later. I don't know. Or maybe we'll identify it now. I don't know. We'll just kind of start talking here. Because again, my goal in teaching is to show you how to think through the process, not to just tell you a series of steps and have you follow along. So this, it sounds awful familiar because we talked about derivatives and their relationship to motion. And so we know that we have the position function can be given as s of t. And that sounds like something we're going to need to know because we're asking how far does the car travel. That's about position. And then to figure out how many seconds before it stops, we're going to need to know probably some of that. Let's see. Velocity is the first derivative of this. So v of t is equal to s primed of t. And then acceleration here is equal to a of t is equal to the derivative of velocity, v primed of t, as we know from prior experience. So what else are we given? We are given that the car is going 88 feet, so given 88 feet per second, and then brakes applied. So this is what? 88 feet per second is a velocity, spelled wrong, and that's the velocity at the instant the brakes are applied. And so this is when we're going to start counting. We're going to start counting time. It's all about slowing down. We're going to start counting time when we start slowing down at time equals 0. So this given information actually gives us a, quote, initial condition. We don't oftentimes write this down as an initial condition, but that's where the name of this process comes from. So this tells us that v of 0 equals the velocity at time equals 0 when we start counting is feet per second, 88 feet per second. So that's kind of nice. And we also know acceleration. And I know I wrote this above, but we're just kind of summarizing things here. Acceleration, we're given that we are decelerating. So we get a negative number here. So we got a of t is equal to negative 15 feet per second squared.
Do you want to go for a walk to the bouncy animal park?
Yes, I do. I want to go to the bouncy animal park, but give me a couple more minutes. Okay, bud?
Can I wait right here?
Yeah, you can wait here, but you got to be quiet. Okay, so we've got our given information, and please forgive me, my little guy's intrusion there. We've got our given information kind of summarized nicely. We'll put it in a box because it's important. That way we can see it easier. And so here's the key idea. The key idea here is what we've been doing this whole time. If we take the integral of a derivative, what do we get? The parent function for that derivative. So let's play with this. And I'm going to get a fresh slide here to start to play with this. Okay, so what could we start with here? Well, the only thing, okay, fresh slide here. The only thing we really know that is like a function is that a of t is equal to negative 15. Okay, so that's a function. Because the other ones, it's really, we don't know the velocity function. We just know a particular velocity at a particular point in time. So the only one of these that looks like a function is this. So how could that fit into our key idea of f of x is the result of the integral of its derivative? Well, we could take acceleration and write it in terms of a derivative. We could write it as the velocity. The derivative of velocity is negative 15. And then we can just this fits into our game. We can integrate the derivative of velocity, acceleration, if you will. And when we integrate that, what will we get? We will get, well, what has the derivative of velocity? Well, velocity has the derivative of velocity. So let's substitute in some values, and we will be able to come up with an expression for our velocity. Negative 15. Okay, so maybe I'm mixing up my t's and x's a little bit here. That should be dt there. Negative 15 dt, because our variable is t. That's something we know how to do with the power rule. Or even just more logically, what has derivative constant negative 15? Negative 15 times t. But don't forget, we've done an indefinite integral there, so we could tack on any constant number there. So now we have a expression for our velocity. So kind of summarize where we're at and what do we know so far. So our velocity, v of t, our velocity function is negative 15t plus c. And we know something. We know velocity at time equals 0 is equal to 88. And we're going to use this to find c. We're going to exploit this to find our particular c value. So 88 is equal to v of 0. Okay, so what is that? That's 88. And velocity evaluated at time 0, well, that's this function above evaluated at time 0, negative 15 times 0 plus c. That gives us that c has to be 0 plus c has to be 88. Putting this all together, now we have a concrete, definitive, single answer, not any of this infinite possibilities for a velocity formula. Velocity is equal to negative 15 times t plus 88. That seems fairly important, so we'll go ahead and circle it. Now, I haven't even really talked about the answers at all, or the questions at all, because this should seem like the problems we were doing just a few days ago at the end of our applications of differentiation unit. And the difference is they are, but we had to do an initial value problem, some integration, to come up with the formulas that we would need to actually answer the question. So now let's tackle the question. We want to know, part A, the time before it stops. Okay, so when does the car stop? Well, the car stops when the velocity is equal to 0. So v of t equals 0. Conveniently, we have a function for velocity. It's negative 15t plus 88 equals 0. Algebra that rig out. T equals 88 over 15, which is approximately 5.9 seconds. Seems fairly reasonable to stop a car going 60 miles per hour in 5.9 seconds. I don't really know. I've never stopwatched it. I hope so. I don't know. Okay. All right. The next thing is we're ready to tackle the distance it travels before stopping. So B. To know the distance, we need some more information. What do we need? We need the position function. So, oh no, we might have to do that. This is actually going to be fun. We need to do another initial value problem or another integration. Just think of it as an integration. Well, we know something about velocity. We know that velocity is equal to the derivative of position. And so our key idea here is that to find the position function, we can integrate the derivative of the position function, which in this case is really just our velocity function. And so our position function is going to be the result of the integral of negative 15t plus 88, my velocity function, with respect to t. And integrating that, we get negative 15 over 2 t squared plus 88, I'm doing my power rules pretty quick here, plus t, times t plus c. So the question is c. We can't have that. We need to figure out we need some way to figure out this, we just got to figure out what this constant is. And then we'll be golden and we can figure this out. So, giving myself a little bit of a fresh page here. So, I don't know. What are you going to start? Well, in the same way that we started braking at time t equals 0 is brakes applied. And we want to know the distance traveled from beyond that position. Why don't we just take our initial position at time 0, to be 0, and then start measuring how far the car goes. That seems like a reasonable thing here. So using this initial condition, now we have something to pair that with our formula of s of t is equal to negative 15 over 2t squared plus 88t plus c. That's going to be 0. S of 0 equals 0. Plug in a 0, get 0 plus c. This tells us that c is equal to 0 in this case. So now we have a concrete position function of s of t is negative 15 over 2t squared plus 88t. And then how far does the car travel before stopping? Well, here it becomes beneficial to remember that the answer to the prior question was time equals 88 over 15 seconds is how long it takes the car to stop. So the position function is going to just track forward how far the car travels during that time, because we know that a velocity never hits 0 but until it actually stops. So this becomes a game of just plugging in s of 88 over 15, the time it takes for the car to stop, will give us the position if we start counting at 0. And leveraging fairly heavily the power of a calculator, 258.133 feet before stopping is how far our car travels. That's it for an introduction to indefinite integrals, antiderivatives, and their application as initial value problems.